Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be working about simplified Bishop method. Okay, this is a very important, method, quite accurate, and usually we use this one for hand calculation to support any computer program. Okay, now you can see here that there the assumption, as you already know, that for limit equilibrium methods, actually you have to have some assumption, otherwise you cannot solve them because the number of unknowns would be more than the number of equation, right? So for simplified Bishop methods, actually the assumption is the interslices forces are horizontal, so there is no vertical component of the forces. Okay, that's the most important assumption here. And then the circular slip surface means like the failure surface is always circular. That's the assumption we take for simplified Bishop method. Now you can see, even though we are saying that the interslices force are horizontal, but this method doesn't account the equilibrium of forces in the x direction. So basically I have, for a slice here is pi, this is pi plus 1, no vertical component, but this method doesn't summarize the forces in the x direction and set that 1 equal to 0. Okay, so if you see here, the total unknown for n slices is factor of safety, which is 1, and the normal forces, which is n. So total unknown is n plus 1. And the number of equation we use the summation of Fy equal to 0, and then summation of a moment for the entire, failure surface, which is actually 1. So total equation equal to n minus 1. So you can see the Bishop's method doesn't satisfy the summation of Fx equal to 0. Now, the simplified Bishop method has been widely used in slope stability analysis and regarded as the best method for limit equilibrium. Okay, these days, even though we use like other methods like Spencer's method or Sharma's method, Morgenstein's method, which are not possible for hand calculation, that's why these days we use the software to solve the problem using that rigorous methods like what I said. But we need to support that one with hand calculation, okay? And most of the cases these days, Bishop method is the one that we use to see whether the output of the software is valid or not, okay? Now, simplified Bishop method is more accurate than the ordinary method of slice, especially for effective stress analysis with high pore water pressure. Okay, if the pore water pressure is low, then basically you will see the ordinary method of slice, and simplified method is basically gonna give you similar factor of safety. Okay, for undrained situation, when phi equal to 0 or total stress analysis, basically simplified Bishop method is essentially same as the Swedish circle or ordinary method of slice. Okay, the primary limitation of Bishop's simplified method is that it is limited to circular slips surfaces only. Okay, we cannot make any other type of slip surface for this particular method. Now let's see what we usually do here. So let's say this is your slope circle here, and I took one of that slice from somewhere here, which has a width of b, and you can see they have only horizontal forces here because that's the assumption of the simplified Bishop method. Here is the weight, there is the normal force here, and this is your shear force here. the bottom surface, in the bottom of that slice, make an angle alpha with the horizontal. On the other hand, actually the top one makes an angle beta with the horizontal. We'll talk about that later on, like that beta angle here. Now, just for simplified case, you can see the mobilized shear force is basically S equal to capital A is equal to small letter s multiplied by del L. This is stress, this is force, okay? But we know that S is equal to tau by F, okay? So if you plug the value of tau here, that gives you C prime del L plus N minus U del L tan phi, where N is the normal force and U is the pore water pressure, okay? Now, if you take the summation of forces, as I said earlier, that this method take only summation of force in the y direction and summation of a moment of the entire slice, okay? Anyway, so if I take the summation of forces in y direction, then you can see the forces is y direction is basically n cosine alpha plus s sine alpha minus w is equal to 0. Okay, so we can just simplify that one and say n equal to w minus s sine alpha divided by cosine alpha. This is equation number 2. So plot the value of s from equation 1 in equation 2. So this is the value of s. You just plug that value here in that equation 2, and then you get this equation here, like this equation, just plug the value of s from here, actually this one here. So you get like this equation, okay? But you can see that we simplified that one because this one is divided by m alpha, while m alpha equal to cosine alpha plus sine alpha tan phi prime divided by f, okay? Now, if you take the moment about O, if you take the moment about O here, then basically you see that summation of moment equal to 0. So W into R sine alpha, W is the weight, and the distance of this one is R sine alpha, minus S into R. So minus S, the total, like force working along that thing here, into R. R is the radius, okay? That's equal to 0. Now from equation 3 and 4, if you just play with these two equations, then basically you get your factor of safety is summation of C prime B. B is the width of that particular slice. W is the weight. Tan phi prime is the friction angle at the bottom of the slice. This is your pore water pressure at the bottom of the slice. I said already B, and then M alpha, which is basically cosine alpha plus sine alpha tan phi prime divided by F, and divided by W sine alpha, okay? The normal cases here, we are just not assuming that there is any external force working on that particular slice, okay? So basically we try for if there is no water there or like little water there, we usually use that equation to find our factor of safety. Now you can see for total stress analysis, if you put your U equal to 0 here, then this term becomes 0. So your factor of safety would be only C prime B plus W tan phi divided by M alpha divided by W sine alpha. For undrained condition, when your phi equal to 0, we said that like, hey, when phi equal to 0, then basically this simplified Bishop methods is very similar to actually your ordinary method of slice method, right? So you can see here, if you put your phi equal to 0, then this part is also 0. So you get C into del L divided by W sine alpha. Okay, so that's basically you get here, which is very similar to your other two methods, like Swedish circle method and ordinary method of slice, actually very similar equation from there. So that's what we are saying here, that for phi equal to 0, the simplified Bishop method is essentially the same as the Swedish circle method or ordinary method of slice. Okay, now how do we solve that equation using spreadsheet? So we just take each of that thing separately, and then try to use the spreadsheet and finally add them together to find out the summation here and summation here. Once you get each of that column here, then basically each of that parameters here, then basically we can find out our F. Now let's take a look at what we get here. Let's say this is for end of construction or short-term stability of an embankment. Okay, so here is basically your embankment. This one has 3:1 slope here, and from here to here you have 2.5:1. The elevation here is 91 feet, here is 0. Okay, the radius is 278. This is your center, which is 101 and 259 from this point here. Okay, this is, let's say, the origin here. So you have to go 259 and then 101. So that's your center. Once you get your center, take a radius of 278 feet and draw that line. That's basically your potential slip surface. We don't know, honestly, we don't know where this one is going to fail, right? So you are going to find out, like in practical case, you just try to find out like at 2-3 different possible ways, like possible failure surfaces, and try to see which one produces the lowest factor of safety. But when you are going to use the software, then basically you can check that one for hundreds of potential failure surface, and then see that which one is the lowest factor, provide the lowest. Actually, the software will provide you, this one will check like thousands in a minute, okay, and then show you that which one shows the lowest factor of safety. Okay, so the lowest factor of safety among that 1,000, like slip surface would be your lowest factor of safety, means like your actual factor of safety for slipping. Okay, now you can see here there is like 2 different layers of soil. One is like here, anything above this elevation, which is actually the embankment, and anything here, this is basically the foundation soil. Now they gave you the material property. This is for embankment and this is for foundation. Total unit weight is 135 here and 127 here. This is your C for embankment, and this is your C for foundation. So you can see from here to here, like 1, 2, 3, 4, 5, up to 5 slices, this one applies, right? And from here to here, basically this one applies. Similarly, from 1 to 5, actually you see the phi equal to 5 degrees. From here to here, actually your phi is 2 degrees. Okay, so you have to be very careful that what soil parameters you are using. That depends on like which the bottom of the slices. Okay, you can also see that when they made that slices, they just put one line here so that you can just use like all those 5 slices, like the same parameters here. Okay, if you make that one at the middle, then basically that would be a little difficult to find out the like the shear force at the bottom of the slide. Okay, so you have to be a little careful when you make your slices. So first of all, you'll try to make like everything um, kind of like a uniform size. Like you see the here, like they make like one slice here. Let's say if they don't make that slice here, just make like a big slice like this, then basically you have a difficult time to find out the area of this one and also the center of gravity of that one. Okay, so that's why you have to be very careful about that. Now, here is the like a spreadsheet. I provided you the blank sheet here so that you can use like very similar way. Actually, I collected that one from the Corps of Engineers manual, slope stability manual. You can just take a look there because you have a copy of that, right? So that's basically the thing here. Now you can see from the beginning, I can say like, hey, 1, 2, 3, 4, 5. These are above that foundation. Okay, so this is slice number 1, 2, 3, 4, 5. For the foundation thing, just we have two part here. Like for number 6, this is your embankment part, and this is your foundation part. For here, this is your, so you just try to find out the area of this one and area of this one separately, and then multiply with the gamma for each of the corresponding value here, and then add them together to find out the total weight. Okay, that's what we try to do here. Like for 6, like the horizontal width is same, which is 26. This is the average slice height, like let's say from here and here divided by 2. So that's the average height. This is the average height for the foundation part. Okay, let's say this is number 6. So this is, we are talking about the average of this one plus this one up to this point divided by 2. That's actually 64. Okay, on the other hand, if you just take like this plus this, that's actually 0. This plus this divided by 2, we only get 5 here. Okay, so this is the area. So that's the area for the embankment, and this is the area for the foundation. So if I multiply that one with the unit weight of the embankment, and then convert that one to kip, or divide that one with 1000, then we just get 240 kip, let's say for 6 here, like this part here, and this part here, which is actually only 16 kip. So we are just adding these two and we are getting the total weight here. Okay, somehow this one is 256. Actually, I ignored the I'm not showing that one actually, the Excel file here, but there is some like 240.6 and maybe like 16.1 or 240.4 and 16.3. So if we add them together, you get the total weight here. Okay. Now you also find out the slope of the sleeve surface at the bottom, which is alpha. So basically we go to the middle point and try to draw that line here and get the angle, measure the angle from there. So that's actually that particular case. You see that this one is actually, got that directly from the example problem that's shown in your manual, like Corps of Engineers manual. Okay, so these are the slope surface. You can see this is -5 and -15. That's actually for this particular one because this slope is negative here. Okay, that's why this one looks like that. Then the base length of the slice, which is nothing but b divided by cosine alpha. I know already W, I know alpha, so I can just find W sine alpha. This is the C and phi value. Okay, so you can see this is basically your 1.78. That's your C because we are converting everything in kip. Here is in pound. Okay. So here embankment, this is your C. For foundation, this is your C. Okay. For fee, this is your fee for embankment. This is your fee for foundation. Okay. Once you get that one, then you just try to find out your CB plus W10 fee, because that's what I need to find out, right? The one part here, then another part here, and another part here. So once I get that one, then basically I can just find out my F. Now you can see here that this one is, we are calculating our MA, but you see that MA is a function of your F. So you have to assume a value of F. Okay. So here, let's say I assume a value of 1.5, 1.75 here. Okay. Now, this one at the beginning, actually, I don't know what is that value of F. So you can just assume any value, let's say 1. Okay. Once you get that one, then basically you can get this part here, which is actually the top of that. And when you summarize everything there, then basically you can get that summation here. That's the top part, and this is your bottom part, which is summation of W sine alpha, summation of W sine alpha. Okay, so your factor of safety is basically this divided by this. Now you can see you have actually F in both sides, because here is M is a function of F. So you have to just try to see that how you can match this one so that your assume F is equal to your calculated factor of safety. Okay. Now let me show you the Excel file that how we can do that one. Okay. So this is actually your Excel file. So you can see if I change the assumed value here, okay, if I change the assumed value, let's say 1, then this one changes. So this one also changes, and these two changes. So you see that my calculated factor of safety is 1.71. So what we do, we just try to iterate that one, and every time I assume the value what I see here. Okay, so if I put 1.71, then you get 1.75. So I'll just change that one 1.75. And now you see that calculated factor of safety is also 1.75. So this one converges, okay, both sides. So it's not that difficult to converge that one, like, because we Excel, like does that one quite easily. In the past, they had like, they had to use a lot of time, like kind of trial and error method. Every time you're changing your assumed value, all those factors are changing, and this one is changing. So this will also change. This one will not change because this is not a function of F, but this part is a function of F because here is your MA, okay, M alpha, which is actually a function of F. So that's the way we usually solve this kind of problem. Now, if I go to this one again here, you can see for each of that column, this is your column number here. And how did I get like these values here? I also showed that one here. Column number 1, you can see, no, this is not the column number. You can see how did you get like 3, 4, 6 in figure, okay? And then you can see that I just wrote a step-by-step procedure. Okay, that's how I'm gonna get that one. Most of them are kind of self-evident, and they can just, you can understand easily that what this one is talking about. But if you are kind of confused, you can read this one to see that how you got one of that column here. Okay, so these are also from your manual, like the Corps of Engineers manual. So you can also see that one from there too. I just tried to summarize that one here. Okay, so you can see like column 15 is here. The new factor of safety is computed from that equation is here. So that's basically the way you have to solve it. Now, it doesn't take that long, like to explain, that one. But basically, when you will try to do that one, you will see you need a lot of time to do that. Okay. First of all, you have to draw that one in your AutoCAD, and then you have to measure, like that each of the parameters, like your alpha, like your B, and then like each of the sides, like the length of the slices, all kinds of things. You have to get that one from AutoCAD. Once you get that values from your AutoCAD, you just try to fill that spreadsheet and see that what, like factor of safety you get, like from there. Okay. Now, let's see another example for long-term or steady state seepage stability analysis. Okay. Now, this one would be a little bit complicated, but very important because we see this kind of situation quite often. Let's see, this is kind of like this. From here to here is 3:1, and from here to here, 2.5:1. The total height is 110. This is 0. And you have water here. Okay. You have water here. So basically, since you have water here, then you will see that there might be pore water pressure there. Okay, this is also an example from your manual. Okay, you can just take a look there. And this is your material properties. The unit weight is 135, C equal to 0, phi equal to 30 degree. Unit weight of water is 62.4. And you can see that that's a different one, and you have several, like 12 actually slices here. Okay. Now, if I go there, what is new here? That's the most important thing. The other one, you can see the slice number. We don't have like foundation or embankment because this one is within the embankment, and they didn't say that the property of that even this touching the foundation, but they didn't say any property of the foundation soil. So we are assuming that it's kind of like same soil everywhere. Okay. So you can see this is like all that 12 slices here. This is the 12 slices here. So everything written in green here, that's basically you get that one from your AutoCAD file. Okay, just measure all those things here. And then you can see the total weight. You just find that one from there. And then base inclination, which is actually here, alpha. And this is your beta here. Okay. You can see from here to here, the beta is same for everybody. Okay. Is that true? No, basically, if I see here, then basically up to from here to here equal to your beta is same, but from here to here, your beta is a little bit different because this is 2.5:1 and this is 3:1. Okay. Now, there is another thing here which you didn't see over there. This is called the surface load, because the water here is actually putting load onto that slide. Okay, here. This is for each of that slide, not each, because you see like from 1, 2, 3, 4 doesn't have any surface load. You can see here that surface load, these are 0, so surface load is 0 for 1, 2, 3, 4. Okay, 1, 2, 3, 4. 1, 2, 3 doesn't have any surface inclination, which is 0, like from here to here. And then 4 started like this way. So you can see 22, 22, 22, 22, and then it's 18, 18, 18, because that's the junction here where you can see this one meets here. Up to 74, 0 to 74, that's actually 18 degrees. From 74 to 110, that's actually 22 degrees. Okay, 18 degrees and 22 degrees. Now, this one is important, that what is your surface load? Okay, the surface load is nothing but the gamma h multiplied by the area of the, like top of the slice. Okay, so that's your surface load. So if you see the formula, that's actually, you can see the average height of the surface water multiplied by gamma W, and then multiplied by B divided by cosine beta. Okay, that's actually how do you get this force here. Okay, once you get that force here, like your P, then you divide that force into two components. One is P cosine beta, and this one is P sine beta. Okay, now you see the distance from here to here, that's actually dH. So we have to measure that one for each of the slices. Okay, and then the distance from the center to this component is dV. Now, any moment that's trying to slide that one, that's actually negative. And any moment that's trying to, kind of counterclockwise, that's actually positive. Okay, which is trying to protect the sliding, that's positive. Counterclockwise is positive, clockwise is negative. Okay, so now you can see my total, like moment would be P cosine beta. That's P cosine beta multiplied by dH, and then plus P sine beta multiplied by dV. Okay, so you can see in that situation, actually your factor of safety when you have surface load here, then this one is summation of C prime B W weight of the slice plus P, that's the surface load, cosine beta minus U is the pore water pressure at the bottom of the slice. And we already said B is the width of the slice, tan phi prime divided by M alpha divided by W sine alpha minus 1 by R summation of moment. Okay, MP. And MP is actually P cosine beta into DH plus P sine beta into DV. Okay, so you can see that these two, you also measured that one actually from your AutoCAD file. Okay, then you try to find out the moment. I just tried to show that one here. So moment is nothing but this is your horizontal, surface load. So this one is P cosine beta multiplied by dH plus P sine beta multiplied by this. Okay, now you can see, you can say like why that horizontal moment arm is negative here. Okay, this one is negative. I put that one again. Distance cannot be negative actually, but they are putting that one negative because this one will create negative moment. Okay, so let's say like we got 1, 2, 3, 4, 5. So from 5 to 9. Okay, so from 5 to 9, 1, 2, 3, 4, 5. This up to this 9. Actually, you can see this one is right side of that point here. So they are trying to, like trying to make that moment, especially for this one, P cosine beta multiplied by DH is trying to rotate this way, clockwise direction. So that's actually negative moment, okay? And this one is always positive moment, right? Because you can see this one is for each of that cases here, 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 here. These are all positive cases. So that's why the vertical moment term is always positive, okay? And this one is for one, like 5, 6, 7, 8, and 9, like all that slices where center is actually right side of that one, and that will try to rotate clockwise. On the other hand, for 10, 11, and 12, let's say there is a force here, this one will try to rotate this way, right? So that's why we just put the negative number, and then basically this is the summation of that two moments. So you get the total moment here, okay? Total moment here. Now you can also see that the piezometric height that actually given for long-term stability, actually you most of the cases get the piezometric height or like the pore water pressure directly measured at the field, because when they construct, they usually put a lot of, like piezometer there. At the beginning, the height of the piezometer would be a little higher because still like consolidating at that time. But long-term means like when all the consolidation has occurred and there is a steady state, flow through the soil. So in that situation, basically you get that value from there. So this value is given. For the homework I assigned you, actually, I gave that line, like the piezometric line, so that you can measure that one directly from there. So once you know that piezometric height, you just get the pore water pressure, which is gamma into gamma W into this height. So that's basically, this one is your pore water pressure. Now I converted that one to KSF, okay? Now you see the cohesion, that's actually for from all 12 slices, the 0 and friction angle is 30. So that's the top part of that equation, okay? Not the whole thing, actually like from here to here, okay? That's here. And then you have your M alpha. You may, again, like you do calculate that M alpha based on assumed factor of safety, 2.16. You don't know at the beginning that it's 2.16. It's always better to assume something 1 or 2, something like that, okay? So you assume that one at the beginning, let's say 1. So you find out your M alpha here, and then finally the top part of this one, okay? Now you see here that this is your summation of this thing here. At the bottom, this is your W sine alpha, and this one is 1 by R here, 1 by R, and then summation of MP. This is a summation of a moment, okay? That's actually MP here, summation of moment. So your calculated factor of safety, this cell is equal to this divided by this minus 1 by R. R is 210, okay? And then summation of this. So that's your calculated FS. So at the beginning, you will again see that your assumed FS is not equal to your calculated FS. So you again try to change that one for several, like trial, you will find out the actual factor of safety. Okay, now again, you can see I just wrote all those things here, and that will tell you like, hey, what's coming from where. Okay, column 2, 3, 6, column 4, column 5. That's are written here, and this is again from your manual. I just tried to summarize that one here. So if you don't understand any of that column, you just go there and then try to figure out how this one is working. Okay. So that's basically the equation we are going to solve at the end. So if you have any question, please don't hesitate to come here during the Zoom session, and we can definitely discuss about that. Now, let me show you the Excel file for steady state seepage case. Okay, so I said that this is your MA. Let's say at the beginning, I assume this one is 1. Okay, so you see everything has changed, and this one has also changed. So basically, your calculated FS is 2.01. So I have to put that one as 2.01. So you see this one is 2.15 now. So I'll try to do that one 2.15. So it's 2.16. So I'll put 2.16. So now you can see this one is close to each other. Okay, it means like this one converged, and by actual factor of safety is 2.16. Okay, so if you just make that spreadsheet, then basically you can take a look like, hey, what's happening down there. Now, one of the important things for your homework is like I asked you to do like in a group, so that you can just make your spreadsheet by yourself, and then you can take a look like how this one, and this one is varying. Okay, if you see that no, they are quite similar, then basically you did the like the problem correctly. This is actually the method the Corps of Engineers have been using, because I have been working for Corps of Engineers as a design manager for a while. And that's what they do. They usually try to do separately 2 different people, and then they try to see which one is there. Like if they get the correct answer, like both of them, then you are fine. Otherwise, they will sit together, try to compare that one, and if see like, hey, there is a difference, then they take a look there, focus on there, that what mistake has been done, okay, and then try to correct that one. So that's the way they work. That's why I just tried, like to make groups so that you guys can work together, so that these values are same for all of you. Okay, these values, that green and red thing, that has to be measured directly from the from AutoCAD. This one is your property. That's also same for everybody. Okay, but this slice thing here, you will see this is actually different for different groups, right? But at the end, we would like to see that actually the summation of, like, let's say W sine alpha, this one has to be quite close for each of the group. For within the group, that has to be same. Okay, if you are different group, then you can see that there might be little difference there. Okay, but honestly, your calculated factor of safety will not like change more than 5%. Okay, it's common like that. Hey, depends on sometimes that how many slices you take. In hand calculation, as we said earlier, that it's very difficult to make too many slices. So usually like 10, 12 slices is fine. But when you do that one in software, then you can usually try to make more than 30 slices. Okay, and then you can take a look, like if you make like 100 slices, actually the, like the result that doesn't differ that much, okay? Usually remains same. So that's our plan. And once again, like if you have any question, please feel free to join me in the in the Zoom session. Okay. Thank you for watching.